How does glue work? Glue is actually a very simple concept. It sticks things together, and we've known about it for a very long time because there is evidence that Paleolithic man knew about glue 200,000 years ago when he used it to stick his collection of beer mats on his cave wall. But given that gluing things together is such a simple notion, explaining it is actually rather complex and a source of controversy amongst boffins who chose to study glue rather than something simple such as particle physics. Firstly, let's ditch the term glue because that could mean something abstract like the social glue. Techie types prefer the term adhesives, so that's what we'll do here. There are several categories of adhesive. They can be reactive, relying on a chemical reaction to make them harden, or non-reactive, not relying on a chemical reaction to make them harden. There can be drying adhesives, pressure adhesives, contact adhesives, multi-part adhesives, and natural adhesives. The first adhesives were, of course, completely natural and made from anything that happened to be sticky, so beeswax, jam, tar, bogies. Then came more complex chemical adhesives, most famously animal glue. And these were made by boiling up whatever was left on the slaughterhouse floor when everything else had gone into the food chain, from posh sirloin steaks right down to the rubbish that we call cat food. So, horses' hooves, for example. In the modern age, the chemical industry has produced sophisticated superglues such as acrylic or cyanoacrylic, or most famously two-part epoxy. Adhesives need to have adhesion, the ability to stick to things, and cohesion, the ability to stick to themselves. Adhesion occurs at a molecular level, and this is where theories are in conflict, because some people say it is all down to mechanical bonding, but others say it's down to something called van der Waals forces. In simple pub bluffers terms, van der Waals forces come into play when molecules are polarized. They have a positive and a negative end, so they attract each other like billions and billions of microscopic magnets. The problem is, we know that van der Waals forces only work when materials are in extremely close proximity. Actually, about 0.1 nanometers. That's a 10 billionth of a meter. So the rival camp thinks that isn't what's happening at all when we glue things together, at least not all of the time. They say there must be an element of mechanical bonding, more specifically something they call mechanical locking. The theory here is that any apparently perfectly smooth surface, a sheet of glass, a pool ball, David Cameron's face, is actually very rough when viewed at a microscopic level. The adhesive therefore works by flowing into these imperfections and locking into the imperfections on both sides. And this explains why rough things stick together better than smooth things. And it also explains why the instructions on many adhesives ask you to key, i.e. rough up, the two surfaces to be joined. The truth is, adhesives probably work through a combination of several or even all of the things I've just described. What we do know is that modern adhesives work extremely well indeed. How does deodorant work? You stink. Sorry to be so brutally honest about this, but it's better that you hear it from me than by finding a growing pile of soap or perfume left for you by your work colleagues or your family members. Your natural aroma is actually the result of various things, including your diet, your genetic makeup, but the primary suspect is the apocrine sweat gland, present in both your armpits and what is delicately termed your genital region. Each of your pits contains up to 50,000 of these glands, and the average human produces a litre of sweat every day. But sweat itself doesn't smell strongly. It's basically just water and various salts. Body odour is the result of billions of microorganisms that live on your skin, mostly bacteria. The majority of these are not harming you and may even offer positive benefits like stimulating your skin's immune system. But some of these, especially members of the Corynebacterium clan, manufacture enzymes that break down your honest, hard-working sweat into a variety of acids. many of which, including propionic and butyric acids, and especially trans-3-methyl-hexiomic acid, stink. Your armpits and your pubic region are also likely to contain thousands of thin, wiry hairs, broadly similar to the ones that Jeremy Clarkson has on his head. And these act to wick this pungent mixture, exposing more of it to the air to help it spread further and faster, and potentially enabling you to clear out a whole room by the simple act of walking into it. Humans aren't alone in having a tendency to make strong smells. Many animals have serious BO too, and in the wild it can be a huge advantage, marking out territory, attracting mates, or repelling enemies. Or even, in the case of those creatures that feign death to avoid getting eaten, to persuade potential predators that they are already rotting and not very palatable. But for humans, smelling strongly is rarely regarded as a good thing. And another problem is that our favoured way to clean ourselves, through the use of soap, can actually intensify this natural aroma. Naturally, our skin tends to be slightly acidic, but soap is alkaline, and using it repeatedly encourages more alkaline-loving bacteria to flock to us, which is where deodorant comes in, killing or suppressing the bacteria through being mildly acidic, and usually also carrying some perfume elements as well to make us smell nicer. It's not a new idea. Naturally occurring deodorizing salts have been used for thousands of years, but it took the marketing departments of big cosmetic companies and the threat that your BO was turning you into the office bogeyman to see the idea really take off. Because modern deodorants don't just make you smell fractionally fresher, they also serve as antiperspirants, reducing the amount you sweat. The modern antiperspirant was invented in the 1940s by a man with the spectacularly French name of Jules Montagnier. Sadly, from the point of view of me now making a cheap gag about the French buying less deodorant than any other developed country, Montagnier was actually from Chicago. So we can't do that. Antiperspirants contain an active ingredient to reduce the amount you sweat and therefore the amount of stink fuel available to the bacteria on your skin. This is almost always an aluminium compound, aluminum for our American viewers. This will usually be aluminium chlorohydrate and aluminium zirconium trichlorodrex, either of which will react with the electrolytes in your sweat to create a thick gel that effectively blocks the top of your sweat glands, and which also acts astringently to cause your pores to contract, both of which will reduce the amount you sweat, and therefore the amount you smell. But is this a good thing? There have been several health scares over the years about antiperspirants, and they were briefly banned in America in the 1970s over concerns about the long-term effects of inhaling some of these aluminium compounds. But more importantly, the antiperspirant is also trying to prevent your body from doing something it does naturally and for good reason, to help regulate your body temperature. It's also treating an effect rather than a cause. Research suggests that even extreme body odor can be reduced through changes in diet and by doing more exercise. But deodorants could also be preventing more than just a few sodden shirts. There's evidence that they can reduce the effect of your pheromones, the chemical markers that we excrete and which help us to attract mates, or even just casual sexual partners. We're stinky for a reason. High Karate and Old Spice never worked as well as good, honest sweat. How does radar work? There are few greater joys than shouting rude words very loudly at a cliff. Not only do you get to hear yourself saying something that would shock your mother, bollocks is my favourite, but you also get to hear it a second time, and maybe a third or a fourth, because as the sound waves produced by your voice reach the surface of the rock face, they come bouncing back to you. This phenomenon obviously is an echo, and once you've substituted radio waves for sound waves, it also pretty much explains how radar works. See? Bollocks. Because, as you'll have noticed, if you stand further away from the cliff you're shouting at, then the noise will take longer to get back to you. Indeed, if you pick your location carefully to be different distances from a variety of cliffs, the same word will come back to you multiple times from all over the place. Radio waves had barely been discovered before it was realized that, like sound or light waves, they too would reflect from solid objects. Initially, this was more of a problem than a solution. The shipboard operators of the early spark gap transmitters noticed that other vessels passing between them and the radio operator they were trying to communicate with caused interference. But it wasn't long before boffins realized the principle could be used to detect things, and the telemobiloscope was born. Okay, so the name didn't catch on. Radar appeared later as an American near acronym for radio detection and ranging. And although patents had been filed in 1904, nobody did much to develop radar for several decades. A French cruise liner being the first ship fitted with an obstacle locating radio system in the 1930s. It was the military that really spotted the potential of radar, with America, Britain, Germany, and the Soviet Union all rushing to develop systems as things looked set to kick off in the 1930s. There were some obvious strategic advantages in being able to detect enemy ships and, especially, aeroplanes. The British chain home system didn't look like modern radar equipment, used a fixed antenna array to send out a wide beam of radar energy, with returns then read by receivers nearby. The time between the signal and its return, based on the known velocity of the radio waves, which is the speed of light, enabled distance to be worked out. And using multiple angled receivers and comparing the different returns on each one enabled both the position and height of the target to be roughly calculated. We almost certainly wouldn't have won the Battle of Britain without radar's ability to tell us where the Luftwaffe was amassing the dirty fuckers. Radar's utility was obvious, and more powerful systems were developed, including the familiar rotating array that pulses a signal and then listens for its return before pulsing another. But the principle remains the same. Shout, listen. Okay, there has been one big development, Doppler radar. This enables the system to detect the speed of a moving object without having to wait for two separate pulses to hit it and be bounced back, which in the case of a really fast-moving jet fighter or missile might take too long. This is where the Doppler effect comes in. This is the way in which the pitch of a wave changes according to the relative speed of the object it bounces off. It sounds complicated, but it isn't. Imagine you've installed a very loud mate a mile away and told him, the variation of our obscene echo experiment, to yell rude words at you for exactly a minute. His voice is carried at the speed of sound. Let's call it a nice round 600 miles per hour, meaning that 6 seconds after he starts screaming, the sound waves reach you, and 6 seconds after he's finished, the sound stops. Easy. But now we're going to install him on the back of a pickup truck, one so quiet you can only hear him shouting. The truck is travelling towards you at exactly 60 miles per hour, or to simplify the maths a bit, for anyone who drags their knuckles numerically, that means it will take him exactly 1 minute to complete the mile. He starts to shout as the truck passes the 1 mile mark and speeds towards you. As before, it takes 6 seconds for the first sound to reach you, and you'll also notice that his voice sounds a little bit higher pitched than usual, which you initially put down to him being a bit of a Jessie. 60 seconds later, the truck passes you, just as your mate finishes shouting. So what's happened? Because he's been travelling relative to the speed of sound, which is serving as an unbreakable absolute here, he's been shouting for a minute, but you've only been listening for 54 seconds. The sound waves have therefore been squeezed, their frequency increased. And as a Doppler radar knows the frequency of the radio wave it sends out, the velocity of which is limited by the unbreakable speed of light, it can work out through the change in frequency coming back whether the object detected is moving towards it or away from it, and at what speed. It's how police radar guns work. Of course, radar doesn't always work. If it doesn't find anything to bounce off, then it won't be able to give a return, which is how stealth systems work. And like any wave, it's possible to cancel it by overlaying it with the opposite wave, or jamming it. Should we save that for another time?
How does a quartz watch work? Historically, all timepieces have always relied on something oscillating. In the case of a grandfather clock, it's a pendulum swinging to and fro. In the case of a mechanical wristwatch or a small alarm clock, it's a sprung balance wheel swinging one way and then the other. Because the time taken for one complete swing or one complete oscillation of the wheel is constant, the period as it's known to physicists, then this can obviously form the basis of a timekeeper. The same is true for a quartz watch. A tiny, tiny quartz crystal, you can think of it as an especially small piece of silicon dioxide, or a grain of sand, is an oscillator. It vibrates. As long as you know the rate at which it vibrates, you can use it to form the basis of a clock. Fortunately, quartz has what are known as piezoelectric properties. That is, if you squash it or bend it, it generates a small electrical current. In extreme cases, piezoelectrics are what are used to create the spark in those barbecue lighter things. As is often the case in physics, and with electrical things in particular, the piezoelectric effect also works in reverse. If you pass current through a piece of quartz, then the piece of quartz will deform. And if you pass a particular amount of current through a very carefully shaped piece of quartz, it will vibrate, it will oscillate. Bingo! You have the beginnings of a timekeeper. Look inside a quartz watch, ideally under very strong magnifying glass, and you will see a tiny little metal cylinder. This contains the quartz crystal, usually shaped a bit like a tuning fork and cut very accurately with a laser, and it's minute. When the current from the watch battery is passed across this, it vibrates, it oscillates, and in most quartz watches, it's designed to oscillate at 32,768 times per second. You will notice that if you halve this number 15 times in succession, you will arrive at the number 1. This is exactly what the electronics in the watch do, halving the 32,768 vibrations per second to arrive at a convenient 1 vibration per second, or 1 Hertz. So the quartz crystal and its electronic minders are now delivering regular pulses separated by exactly 1 second. And that is why the second hand on a quartz watch moves in 1 second steps, rather than smoothly and continuously like the second hand on a mechanical watch. It's now a simple matter to arrange gears from that second hand to drive the hour hand and the minute hand in the correct ratio. And we've known how to do that bit for centuries. The basics of quartz timekeeping have been known for over 100 years, and by the 1930s, this method was being used to measure things like tiny variations in the rotational speed of the Earth. But these instruments were massive and very, very expensive. It was during the electronics revolution of the 1960s that quartz technology finally made its way into a wristwatch, and the very first one, the Seiko Astron of 1969, was also very expensive, the equivalent in today's money of about $8,000. But, as with everything else electronic, the price of the innards tumbled to the point of disposability. The great advantage of quartz is that it's incredibly accurate compared with old school mechanical watch technology. Even a really cheap quartz watch can be accurate to within 5 seconds a month, whereas an officially certified Swiss chronometer is only guaranteed to be that accurate over a day. Time, as we know, is money, but thanks to quartz, it's a lot less money than it was. Is there plasma in a plasma TV? Yes, there is. The bigger question is, what exactly is plasma, and how does it help you to watch Strictly Come X Factor out of here in glorious high definition? Well, the technology behind the television barely evolved for the first 60 years of its existence. It relied on the cathode ray tube, basically a device that could fire out a stream of electrons onto the back of a fluorescent screen. The parts of the screen being hit by electrons would then glow, and the beam of electrons would run across the screen in a series of parallel lines multiple times each second. This happened so quickly that our eyes, looking from the other side of the screen, see a steady image. Early televisions had only one of these electron guns, meaning their images were in what was called black and white. Actually green and grey for anyone old enough to remember. But then colour television was invented, giving a new best thing since to replace sliced bread, and that was by using 3 separate streams of electrons to create red, blue and yellow, which could then be combined to enable people to finally make sense of televised snooker. But as our appetite for bigger TVs and sharper images developed, so the humble cathode ray tube screen started to hit problems. Televisions were already heavy, electricity-hungry things, but as the size of screens increased, they had to become deeper as well, so that the CRT tube could reach each corner of the screen. The number of pixels that a CRT could support was also limited by the need for it to scan the whole screen 50 or 60 times a second. This was clearly a problem in need of a solution. The concept for the plasma display had been invented as long ago as the 1930s, with a single-colour plasma display being produced in the 1960s and 1970s, especially for early computers. The principle is very simple. Instead of using a beam of electrons to create lines, the plasma screen uses what are, in effect, tiny, quick-acting fluorescent light cells to form a picture. In a modern colour plasma display, each pixel has 3 of these fluorescent lights, one in each primary colour, and fires them intelligently to create the desired colour in the picture. LCD televisions, the sworn enemy of plasma systems, according to the bloke in the telly shop, use individual LCD shutters for each pixel to create a similar effect. But what is plasma? A plasma is basically just an electrically conductive gas that contains both free-flowing ions, positively charged atoms, and electrons, which are negatively charged. If you introduce more electrons by putting a voltage through this gas, then these will begin to collide with atoms, knocking off other electrons and turning them into ions. Then, negatively charged particles will start to move towards the positively charged area, and vice versa. This causes the atomic equivalent of a motorway pileup, with particles smashing into each other and, with the xenon and neon gases used in plasma screens, releasing photons, or light as we'd call it. Most of this light is ultraviolet, which is invisible, but by coating those tiny cells with phosphoric material, this can be changed into visible light when it hits the side of the cells, which it does a lot. A modern high-definition display with 1920 pixels across and 1080 up has over 2 million individual pixels, each being fired dozens of times a second to produce different colours. The result is that plasma displays are far more shallow than the old CRTs. You can stick them on the wall, but also that they can be scaled up simply by adding more pixels and enough computing firepower to run them. Plasma TVs have been produced in sizes up to 152 inches. That's the diagonal measurement across the screen. Large enough for even the most discerning rap star to watch himself waxing misogynistic in glorious high definition. But now settle down with the Blu-ray release of Ghostbusters and remind yourself how important it is to never, ever cross the streams. Now, if you haven't already gone what my mother would have called square-eyed through watching all this stuff about television, why not go over to Number Hub and find out just how many pixels can be squeezed into the world's largest TV. Do that by clicking here. How does a bulletproof vest work? In many ways, the idea of bulletproofing is older than bullets. The notion that you could protect yourself against your enemy's weapons goes all the way back to the plate armour and chainmail of the medieval knights. Further back than that, in fact, it goes back to the leather armour of Roman soldiers. All this stuff was quite good against swords and battle axes. Trouble was, as weapons became more powerful and more accurate, so armour had to become tougher, and that meant heavier. By the time the first gunpowder muskets had reached Europe, it had all got a bit out of hand, and the average weight of armour went up from 15 kilograms in the 15th century to something like 25 kilograms by the late 16th century. Eventually, we arrive in the late 19th century and the homemade armour used by Ned Kelly and his gang. Each suit weighed around 45 kilograms, which means that one outlaw's energy was almost entirely consumed humping his own protective kit around. None of it left for robbing. Bulletproofing didn't need to be heavier, it actually needed to be a bit cleverer. In fact, it needed to be softer. A bit of physics. A bullet works by concentrating a great deal of energy, all the energy from its speed and its momentum, into a very small point. That's why it can punch its way through apparently impenetrable surfaces like brick walls. And yet, remarkably, you can stop one with fabric. This was worked out by some Koreans in the 1860s who realised that you had to increase the area that the bullet works against. Bullets intended for soft targets, such as animals and indeed Korean soldiers, work by deforming on impact. This increases the bullet's area and allows it to do more damage. But it's also the bullet's weakness, as the Koreans worked out whilst being shot at by the French. They worked out how to make lightweight protection from layers of folded cotton, causing the bullet to deform just before it reached flesh and blood, and causing the energy to be dissipated as it tried to force its way through the lower levels. When the Americans fought the Koreans quite soon afterwards, they captured one of these vests and took it home for analysis. It worked, and the idea quite quickly spread. Interestingly, Archduke Ferdinand of the Austro-Hungarian Empire was wearing one of these bulletproof vests when a nationalist Serbian assassin shot him in 1914. Unfortunately for the Archduke, the assassin had the good sense to shoot him in the neck, thus starting the First World War. By the 1920s, bulletproofing was positively hip in America, where organised criminals adopted these gangster vests to protect themselves against rival gangs and, of course, the feds. This led to a sort of arms race, with more powerful ammunition being developed to penetrate better bulletproof vests, leading ultimately to the development of the notorious Magnum round. Providing protection against relatively slow handgun bullets isn't such a problem. It's reckoned that since 1973, over 3,000 US police officers have been saved from serious gunshot wounds by ballistic vests. The problem is trying to provide protection against high-velocity rifle rounds and bits of shrapnel, as found on the battlefield. Fabric vests simply aren't good enough for this, so modern body armour incorporates metal or ceramic plates as well. So now, once again, we come up against the age-old problem of weight. A modern body armour vest can weigh as much as 15 kilograms. Or, if you remember, exactly the same weight that your medieval knight had to cart about. How do noise-cancelling headphones work? If you're wearing a pair of headphones on a long aeroplane flight, there are two sounds of interest to you. Whatever it is you're trying to listen to, and the tiresome drone of the engines. The sound of the engines is coming from outside the headphones. Girls are loud from within. The genius of noise-cancelling headphones is that they can get rid of the sound of the engines without interfering with the so-called music. All sound is really just compression and rarefaction of the air around us. When you fire a starting pistol, the air around the gun is compressed, then it thins out again, then it's compressed again, and so on. Imagine an infinite number of slinkies stretching away in all directions, and the sound rippling along them. These are known as longitudinal waves, but for the purpose of illustration, we can represent them with sine waves, with peaks and troughs like ripples in a pond. The engines of the aircraft produce a sound wave of constant amplitude, that is the height of the peaks and the depths of the troughs, and constant wavelength, that is the length of the entire wave. And if you produce another sound with the same amplitude and wavelength but opposite phase, that is, it has a peak where the original sound has a trough, you have something called an antiphase. The two cancel each other out, and the result is silence. Weirdly, you add two things together but arrive at nothing. But think of it as adding +2 to -2. So, noise-cancelling headphones incorporate a tiny microphone that listens to the ambient noise, in this case the jet engines. Their internal electronics then measure this and work out an antiphase. But of course you don't hear the antiphase, you hear nothing. And because these microphones aren't listening to the sounds inside the headphones, your music is unaffected. Noise-cancelling headphones are much better at dealing with continuous noise, like jet engines, than they are at coping with sudden or abrupt sounds, so they don't work very well in a gunfight or Prime Minister's question time. When you switch your noise-cancelling headphones on, you will notice a very short delay before they take effect. This is the electronics measuring the ambient sound and coming up with the antiphase. They can't do it immediately. Headphones like this were first devised in the 1970s, but by then the technology was already well understood. Noise-cancelling systems had already been incorporated in the cockpits of aircraft and helicopters. More recently, it's become popular with car makers. Not only can active noise cancellation make a car quieter by playing an antiphase through the stereo speakers, it can actually improve the sound. A sophisticated system can replace engine noise with something nicer, so you can drive around in a dreary four-cylinder diesel hatchback, but enjoy the soundtrack from a V12 Ferrari racing car. This sort of thing is expensive, but then again, a Ferrari 250 GTO recently sold for $35 million. How do digital cameras work? The camera is one of those wondrous inventions that changed the world. Before it arrived, the only way to make a picture was to draw it or paint it, which obviously removed a fair amount of the spontaneity when you were trying to knock off a quick selfie of yourself giving epic duckface while eating a Mackie D's with your bezzy mates. It's probably why Rembrandt always looks so depressed in his self-portraits. Anyway, the camera made it possible to make an instant picture in a fraction of a second, but the process involved in getting the image out of the camera and printed was a complicated one. The light-sensitive film had to be carefully removed, sent to a processor, get developed, turned into a negative, and then printed onto photographic paper in the dark, which was a problem with the rise of the digital age and the internet and your pressing need to upload a picture of Fluffy to the My Cat Looks Like Hitler web forum. But while the microprocessor revolution started to transform many parts of our lives from the 1970s onwards, the digital camera was a relatively late invention, arriving after the video camera, the mobile phone, the laptop computer, and even the Billy Big Bass singing plastic fish. This was because the technology that lies at the heart of it, the sensor chip, is unbelievably complicated. In a film camera, light is sent through a lens and a shutter onto photosensitive film, which, with a subject shot in normal light, needs just hundredths of a second of exposure to capture the image. The front end of a digital camera works on exactly the same principle. Light is focused through the lens and controlled by a shutter and a variable aperture. But instead of film, there's a light-sensitive sensor chip that has to record all of the data in a very short space of time. There are different ways of doing this, but we're going to concentrate on the CMOS, or complementary metal oxide semiconductor sensor, that now sits in the majority of digital cameras, from those integrated in phones to fairly chunky DSLRs. That's digital single lens reflex in the jargon. They're the sort that look like real cameras. The camera sensor is covered with tiny individual light-sensitive cells, each of which can measure the amount of light that falls on it. As the digital camera has evolved, so have the number of these pixels on the surface of the sensor. 10 years ago, you'd struggle to get a digital camera capable of delivering much more than a single megapixel of resolution, 1 million total pixels, or a grid 1200 by 900. But these days, 12 or even 16 megapixels are commonplace among top-spec prosumer and professional cameras. That's enough to enable you to produce images the size of a magazine cover with no loss in perceived quality. The cells act like the photosensitive chemicals on old-fashioned film, reacting to the light that falls on them and then reporting that to the camera's microprocessor brain. That would be fine for the sort of moody black and white shots favoured by gothy Instagram users, but because most of us want to post pictures of our lunch to Facebook in colour, it's also necessary to split the light seen by the camera into the 3 primary colours, which can then be used to create an accurate image. There are different ways of doing this. Some expensive cameras will employ 3 different filters, but most CMOS sensors will use what's called a Bayer filter. This is a grid of coloured filters that sits over the sensor with red, green and blue elements over individual pixels, and they will only allow their respective light colour through. Because the human eye is most sensitive to green light, which largely determines how bright an image looks, there are twice as many green pixels as red or blue ones. The filters are arranged in a clever mathematical pattern, which means that the camera's brain can interpolate using a demosaicing algorithm. Yes, really. Or, slightly plainer language, the camera doesn't just look at an individual pixel on the sensor, it also looks at the pixels around it to come up with an informed guess of what the true colour of that pixel is. Although, even the most advanced sensors in the world still struggle with the increasingly unlikely colour of Richard Hammond's hair.